Welcome to VCE Master Academy. Last lesson, we built a gradient machine. One rule, and it could differentiate any positive power of x. Today, the machine gets an upgrade because it turns out the very same rule also handles negative powers. A negative power just means the x lives downstairs, in the bottom of a fraction. Functions like 1 over x or 5 over x squared. They look scary. They are not. Here's our goal. Learn to rewrite any fraction of that kind as a power of x. Differentiate it with the rule you already own. And find the gradient of a tangent on these new curves. Exam style. Slow and steady. Let's begin.
First, a 1-minute refresher, because everything today stands on this. If f of x is x to the power n, the derivative is n times x to the power n minus 1. The derivative, remember, is the gradient machine. Feed in any x value, out comes the steepness of the curve at that exact spot. The dance move, in plain words. The power jumps down the front as a multiplier. Then the power itself drops by 1. Down the front, drop by 1. Quick warm-up. X to the 4 becomes 4x cubed. 6x squared, the 6 weights. Then 2 times 6 gives 12x. And the constant 7, a flat line, differentiates to 0. Now, so far we've only used this rule when n is a positive whole number. Today, we ask a bold question. What if the power is negative? Hold that thought. So what is a negative power? Here is the whole meaning in one line. X to the negative n is 1 over x to the n. That's it. It's not a mysterious new object. It's a fraction in disguise. Think of a fraction as a little house. The top is upstairs. The bottom is downstairs. A negative power simply means the x lives downstairs, in the bottom of the fraction. The minus sign in the power is just the address label. Watch. X to the negative 1 is 1 over x. X to the negative 3 is 1 over x cubed. The size of the power tells you which floor. The minus tells you it's the ground floor, downstairs. And we can walk the other way too, and this is the skill we'll use constantly today. 1 over x to the 5 becomes x to the negative 5. 5 over x squared becomes 5 times x to the negative 2. One careful spot. In 5 over x squared, only the x is downstairs. The 5 is an ordinary multiplier, and it stays upstairs, out the front. Rewrite the x, keep the 5. Get comfortable with this two-way translation, because it's half of today's lesson. Now the big moment of the chapter, and it's wonderfully small. The exact same rule, power down the front, drop by 1, works when n is a negative whole number too. No new rule to memorize. The machine you already own just got a bigger engine. There is one honest condition. X cannot be 0. Look at the curve of 1 over x on the right. At x equals 0, we'd be dividing by 0, which is impossible, so the curve simply doesn't exist there. Two separate branches and a gap in the middle. So, whenever we differentiate a negative power, we quietly say, for x not equal to 0. Watch the rule work. X to the negative 2. The negative 2 jumps down the front. Then the power drops by 1. Negative 2 minus 1 is negative 3. So we get negative 2, x to the negative 3, which is negative 2 over x cubed. And there's the one trap of the whole day. Drop by 1 means subtract 1. Negative 2 minus 1 is negative 3, not negative 1. The power gets more negative. Watch that step like a hawk, and this chapter is yours. First worked example. As gentle as they come, differentiate x to the negative 3. One single term, already written as a power, no rewriting needed. We want the derivative. Same rule as always, and we note x can't be 0. The power jumps down the front, negative 3. Then drop by 1. Negative 3 minus 1 is negative 4. So f dash of x is negative 3 x to the negative 4. Say that subtraction out loud every time. Negative 3 minus 1, negative 4. Last step, and make it a habit for life. Translate back into fraction form for the final answer. X to the negative 4 means x to the 4 lives downstairs. So the answer is negative 3 over x to the 4, for x not equal to 0. Box it. Power form for working, fraction form for answers. That's the rhythm of this whole chapter. Second example, and this is the shape most exam questions arrive in. 1 over x and 5 over x squared, both written as fractions, x living downstairs. We want both derivatives. Here is the golden strategy of Chapter 17c. Never differentiate a fraction as a fraction. Rewrite it as a power first, then feed it to the machine. Rewrite, then differentiate. Every time. Part A. 1 over x is x to the negative 1. Now the machine. Negative 1 jumps down the front, and the power drops to negative 2. Negative 1. X to the negative 2, which is negative 1 over x squared. Part B. 5 over x squared is 5 times x to the negative 2. The 5 weights, exactly like a coefficient always does. Negative 2 jumps down, power drops to negative 3. Then the 5 multiplies in. 5 times negative 2 is negative 10. Negative 10. X to the negative 3. Translate both back to fractions and box them. Negative 1 over x squared and negative 10 over x cubed for x not equal to 0. Notice both came out negative. On these curves, that's no accident, and you'll see why on the graph shortly. Third example. A proper exam-sized function. 3x squared minus 2 over x plus 4 over x cubed. A mixed family. 1 term upstairs, 2 terms downstairs. We want the derivative of the whole thing. Step 1. Translate everything into power language before touching the machine. 3x squared stays as it is. Minus 2 over x becomes minus 2, x to the negative 1. Plus 4 over x cubed becomes plus 4, x to the negative 3. Step 2. Walk along term by term, exactly like any polynomial. 3x squared gives 6x. Now the careful one. Minus 2, x to the negative 1. Negative 1 jumps down and multiplies the minus 2. Minus 2 times negative 1 is plus 2. The sign flipped. Plus 2, x to the negative 2. Then 4, x to the negative 3. Negative 3 times 4 is negative 12. Power drops to negative 4. Translate back and box it. 6x plus 2 over x squared minus 12 over x to the 4 for x not equal to 0. That middle term is the money moment. A minus times a minus made a plus. Downstairs terms flip their signs when you differentiate, and examiners love checking whether you know it. Now we put the upgraded machine to work. A tangent, remember, is a straight line that just touches the curve at one single point, matching its direction perfectly. We want the tangent's gradient on y equals 4 over x at x equals 2. We're given the curve and the location. We need one number. The derivative, evaluated at 2. 3 beats now instead of 2. Rewrite, differentiate, substitute. Rewrite. 4 over x is 4, x to the negative 1. Differentiate. Negative 1 jumps down. 4 times negative 1 is negative 4. Power drops to negative 2. So dy dx is negative 4 over x squared. Substitute x equals 2. 2 squared is 4. Negative 4 over 4 is negative 1. The gradient of the tangent at x equals 2 is negative 1. Box it. Now look at the picture, because it tells you something lovely. The curve is sliding downhill, so of course the gradient came out negative. In fact, negative 4 over x squared is negative for every single x, which means this curve goes downhill everywhere, on both branches. When your algebra and your picture tell the same story, you can walk into the exam calm. Now the 8R level question, and notice the flip. Last board they gave us the x and asked for the gradient. Now they hand us the gradient, negative 1, and ask, where on the curve does that happen? Same curve family, reversed direction. And they want coordinates. That word means x and y, both. Half the marks live inside it. The plan. Build the derivative, set it equal to negative 1, solve for x, then fetch each y from the original function. Rewrite and differentiate. 9 over x is 9, x to the negative 1. Negative 1 down the front, 9 times negative 1 is negative 9. Power drops to negative 2. F dash of x is negative 9 over x squared. Set it equal to negative 1. The minus signs cancel from both sides, leaving 9 over x squared equals 1. So x squared equals 9. And careful, right here is the classic lost mark. X squared equals 9 has two answers, positive 3 and negative 3. 1 point on each branch of the curve.
Now the y values, always from the original function, never from the derivative. At x equals 3, 9 over 3 is 3. At x equals negative 3, 9 over negative 3 is negative 3. So the points are 3, 3, and negative 3, negative 3. Box them. Look at the picture. One tangent on each branch, perfectly parallel, because equal gradients mean parallel lines. That symmetry is exactly what the examiner is testing.
One more costume to greet. The question says, if y equals 1 over x squared, find dy dx and its value at x equals 2. Quick reminder from last lesson. Dy dx is Leibniz notation, and it reads, the derivative of y with respect to x. In plain words, how fast y changes as x changes. It is not a fraction, it's one single symbol, and it means exactly the same thing as f dash of x. When the question writes y equals, you answer in this costume. The machine doesn't care about costumes. Rewrite. 1 over x squared is x to the negative 2. Negative 2 down the front, power drops to negative 3. Dy dx equals negative 2 over x cubed. Now the value. Substitute x equals 2. 2 cubed is 8. Negative 2 over 8, and always simplify your fractions, is negative 1/4. Box both. A formula, then a number. And notice how small that gradient is, 1/4 of a unit downhill. Far from the origin, these curves flatten out towards the axis, and the derivative is quietly telling you that story in numbers. Why does anyone need negative powers? Because nature adores them. Light, sound, gravity, they all follow the inverse square law. Strength equals some number divided by distance squared. Say a lamp's brightness is 100 over d squared, where d is your distance in meters. Distance is always positive, so d is greater than 0. At 1 meter, brightness 100. At 2 meters, 25. Double the distance, quarter the brightness. Now ask a sharper question. As I walk away, how fast is the brightness falling, right now? How fast something changes is exactly what a derivative measures. So differentiate. 100 over d squared is 100, d to the negative 2. Negative 2 down the front. 100 times negative 2 is negative 200. Power drops to negative 3. The derivative is negative 200 over d cubed. At 2 meters, that's negative 200 over 8, which is negative 25. Brightness is dropping at 25 units for every meter you step back. The minus sign is the physics. It says falling, not rising. And look at the curve. Steep plunge up close, gentle fade far away. And the derivative puts an exact number on that steepness at every step. Photographers, sound engineers, and satellite designers use this exact derivative every working day. Let's gather it all up. A negative power is just a fraction in disguise. The x lives downstairs, and the minus sign in the power is the address label. The star result of the chapter, the one rule you already knew, power down the front, drop by 1, now works for every whole number power, positive or negative. The only condition is x not equal to 0, because nobody divides by 0. The workflow never changes. Rewrite the fraction as a power. Differentiate with the machine. Then translate the answer back into fraction form, simplified. Power form for working, fraction form for answers. Trap number 1. Drop by 1 means subtract 1, so negative 2 becomes negative 3. The power gets more negative. Trap number 2. When a downstairs term carries a minus sign, the negative power multiplies it and the sign flips. Minus 2 over x turned into plus 2 over x squared, remember. And the classic mark saver rides again. When a question asks for coordinates, the y value always comes from the original function, never from the derivative. If any line up there feels wobbly, scrub back to its board. That's exactly what the video is for. Your turn. 4 questions, 1 per skill from today. Question 1. 2 single terms, 1 already in power form, 1 that needs rewriting first. Question 2. A mixed polynomial with upstairs and downstairs terms. Rewrite everything, then term by term, and watch those signs. Question 3. A tangent gradient. Rewrite, differentiate, substitute, and simplify the final fraction. And question 4. The ATAR one. They give the gradient, you find the points. Coordinates means x and y both, and remember how many answers x squared equals a number really has. Pause the video here and work through them slowly. Full answers are on the next 4 boards, 1 question each, but don't peek until your page is full. Understanding first, speed later. Let's check your work, slowly. Question 1. Part A, x to the negative 5. Already in power form, so straight to the machine. Negative 5 jumps down the front, and the power drops by 1. Negative 5 minus 1 is negative 6. Negative 5, x to the negative 6, which is negative 5 over x to the 6. If you wrote x to the negative 4, you added 1 instead of subtracting. Drop by 1, more negative. Part B, 3 over x. Rewrite first, always. 3, x to the negative 1. The 3 weights. Negative 1 down the front. 3 times negative 1 is negative 3, and the power drops to negative 2. Back to fraction form and box them both. Negative 5 over x to the 6 and negative 3 over x squared, for x not equal to 0. If both landed in fraction form with the right signs, you've got the core skill of this whole chapter. Question 2, the mixed family. Step 1, translate. 2x cubed stays. 5 over x squared becomes 5x to the negative 2, and minus 1 over x becomes minus x to the negative 1. Step 2, term by term. 2x cubed gives 6x squared, old faithful from last lesson. 5x to the negative 2. Negative 2 times 5 is negative 10, power drops to negative 3, and the sneaky one. Minus x to the negative 1. Negative 1 jumps down and multiplies the minus already there. Minus times minus is plus. Plus x to the negative 2. If your middle-of-the-night instinct said that term stays negative, this board is your correction. Translate back and box it. 6x squared, minus 10 over x cubed, plus 1 over x squared, for x not equal to 0. 3 terms in, 3 terms out, and the whole battle was fought in the signs. Question 3, the tangent. Rewrite. 6 over x is 6, x to the negative 1. Differentiate. 6 times negative 1 is negative 6, power drops to negative 2. dy dx is negative 6 over x squared. That formula holds the gradient of every point on the curve. Now, substitute x equals 3. 3 squared is 9, negative 6 over 9. And here is where a careless mark escapes. Simplify. 6 and 9 share a 3, negative 2/3. The gradient of the tangent at x equals 3 is negative 2/3. Box it. If you wrote negative 6/9, the maths was right, but the finish was scruffy, and exams pay for the finish. Always hand your fraction in fully simplified. And notice, negative again. Downhill everywhere. These curves never climb. And the 8R finisher. Question 4. Build the machine first. 16 over x rewrites to 16 x to the negative 1 and differentiates to negative 16 over x squared. Set it equal to negative 4, the gradient they gave us. The minus signs cancel from both sides. 16 over x squared equals 4. Multiply both sides by x squared and divide by 4, and x squared equals 4. 2 answers, positive 2 and negative 2. If you only found positive 2, that's the single most common lost mark in this style of question, so circle it in your notes. 1 point lives on each branch of the curve. Now the coordinates, from the original function, never the derivative. At x equals 2, 16 over 2 is 8. At x equals negative 2, 16 over negative 2 is negative 8. So the points are 2, 8, and negative 2, negative 8. Box them. 2 parallel tangents, 1 on each branch, both sliding downhill at gradient negative 4. If all 4 questions landed, brilliant. If one wobbled, its board is a scrub away. Great work today. You walked in with fractions that looked untouchable, and you walked out with one rule that eats them all. Rewrite so the x moves upstairs. Differentiate down the front and drop by 1. Then hand the answer back as a clean, simplified fraction. The machine from last lesson didn't change. It just learned a bigger family of curves. Next time, we point that machine at rates of change out in the real world, where these gradients start earning their keep. Until then, you're mastering VCE Maths, one concept at a time. See you next time.